Hi everyone, my name is Arissa and I'm one of the chemistry tutors with Lanterna. Today we're going to be looking at acids and bases, specifically 8.2, which is the second SL subtopic. This subtopic is mainly about reactions concerning acids. So there are three main reactions that the IB wants you to know about. Acids react with metals, they react with metal carbonates, and they react with bases. So we're going to be looking at each of these reactions in turn. Firstly, acids and metals. It's always worth knowing the word equations. Essentially, what are the products that are formed when an acid reacts with a metal? So in this case, it's going to be a salt and hydrogen. If you're ever asked in a paper 2 question, what can you observe when a strip of magnesium is dropped into a beaker of hydrochloric acid, your main observation is going to be that you notice bubbling or effervescence. When asked about an observation, you should never say that you observed hydrogen being released because you don't know that it's hydrogen, you only know that it's a gas. Okay, so that's kind of one thing to bear in mind in terms of qualitative observations. Let's have a look at some chemical reactions then. So our first reaction is magnesium and nitric acid. We're going to go through how you can balance these together. So magnesium is a metal, nitric acid is an acid, so we know that it's going to make a salt and hydrogen. So automatically you know that we're going to get a salt and we're going to get hydrogen. The salt is always going to be composed of the metal and the non-metal. So in this case, the metal is magnesium and the non-metal that we're going to use is the nitrate ion. So the non-metal bit always comes from the acid. So our salt is going to be MgNO3. The next question that you've always got to ask yourself though, is this balanced? So let's look at the charges in order to determine that. So Mg has a charge of 2+, and NO3 is a polyatomic ion that has a charge of 1-. In our previous video, we went through the list of polyatomic ions that are really worth memorizing for your exam. So the nitrate ion, NO3-, is definitely one of them. So now we've got a charge of 2+ and a charge of 1-. This isn't quite balanced. We need to make sure that we've got 2-, and so the way that we can do that is by converting that to MgNO3 2. So what that means then is that we also have to add a 2 in front of our nitric acid because we know that we're going to need 2 lots of your nitrate ion over there. So that's going to be your balanced reaction for the first one. Let's look at the second one. So now we've got zinc, which is Zn, and phosphoric acid, which is H3PO4. And again, we know that we're going to make salt and hydrogen, so I'm just going to put plus H2 there already. And remember, the salt is going to be always composed of a metallic bit and a non-metallic bit. So we're going to have ZnPO4. Let's look at whether these balance out though. So Zn has a charge of 2+. I'll tell you why in a second. And PO4 is another polyatomic ion that's worth remembering, and its charge is 3-. So when we balance this out, we've got to look for the lowest common denominator, which in this case is going to be 6. So what we need to do to make these charges add up to +6 and -6 respectively is we put a 3 in for our zinc, and then that makes the overall charge 6+. And then we put brackets around our PO4 and we put a 2 there, which makes our overall charge over there 6-. So that's your balanced out salt. Now let's have a look at balancing the reactant side. So I know that I've got 3 zinc atoms in this compound. So I'm going to go over here and I'm going to add a 3 to my zinc. And I know that I'm going to have 2 phosphate ions, so I'm going to add a 2 in front of my phosphoric acid. That leaves me with 6 hydrogens, and therefore I'm going to have 3 hydrogen molecules on my product side. Good. Last thing that's worth bearing in mind, how do you name this salt over here? So the salt is named like this, so zinc phosphate. So again, we're starting off with the metal, and then we've got the non-metal, and you're naming the phosphate ion essentially. So if I give you another example, if we look at the salt over here, this is going to be magnesium nitrate. Okay, good. All right, let's look at our last example then. Silver and phosphoric acid. Okay, so I've put this in as a bit of a trick question of sorts. What if I told you that silver doesn't react with phosphoric acid? And you might be asking, how do I know that? All right, let's have a look at your data booklet then. So what I'm looking at now is section 25, which is the activity series. What you'll notice is that hydrogen is also in this activity series that you've been given in your data booklet. Some metals, such as zinc and magnesium that we looked at earlier, are above hydrogen, and therefore these metals are more reactive than hydrogen. But there are other metals that are actually below hydrogen, so less reactive than hydrogen, and one example of which is silver. So if we go back to the slide earlier, any metal that is less reactive than hydrogen on the activity series will not react. So essentially here, you would notice no bubbling, no effervescence, because it would not release any hydrogen. Good. All right, let's look at this slide for a second. So earlier, I looked at the charges of the metals. Specifically, I said that zinc was 2+ and magnesium was 2+. This is section 9 in your data booklet. And actually, this table is really, really useful because it gives you all of the possible charges of your metal ions. So this is going to make balancing equations a lot easier. So it's worth definitely being familiar with this table. Okay, so let's move on to the next part then. So now we're looking at acids reacting with metal carbonates. As always, it's always worth starting off with the word equation. So in this case, acids and metal carbonates are going to make a salt, carbon dioxide, and water. It's worth remembering that all reactions with acids make a salt. So you should always remember that as a product. Now that we're releasing carbon dioxide here, another qualitative observation that you would notice would be bubbling or effervescence again. So let's do the same and do a little bit of balancing out. So calcium carbonate and hydrochloric acid. So calcium carbonate is CaCO3. The carbonate ion has a charge of 2-. It's another polyatomic ion that's worth being familiar with. And calcium has a charge of 2+. So that's nice and balanced out for us already. Hydrochloric acid is going to be HCl, and therefore we're going to make a salt, carbon dioxide, and water. I quite like writing out the formulas for carbon dioxide and water to get to start with, just because it helps you lay out your equation a bit better. Let's look at what your salt is going to be in this case then. So remember from earlier, we said that your salt would always have a metal and a non-metal, so it's going to be CaCl. The next question that we're going to ask ourselves is this balanced? So Ca has a charge of 2+, Cl, because it's in group 7, has a charge of -. So that's not going to be balanced. So the way that we can balance this out is by adding a 2, so CaCl2. This salt is going to be called calcium chloride. Perfect. And then we're going to add a 2N over there because we've got 2 chlorines on our product side. So to finish that up, I'm just going to check that everything adds up. So I'm going to have the same number of atoms on the left side as on the right side. And I do. So this is your balanced reaction for calcium carbonate and hydrochloric acid. Let's look at another example. So now I've got sodium carbonate, so NaCO3. And now I've got to look at balancing again. So Na in group 1 has a positive charge, CO3 has a charge of 2 minus. So I'm going to add a 2 here to balance out this charge to make it 2 plus, so that they kind of equal out essentially. And phosphoric acid, which is going to be H3PO4. So again, I'm going to lay it out. I've got my salt, I'm going to have carbon dioxide, and I'm going to have water. Good. All right, so my salt, yet again, is going to be composed of a metal and a non-metal. I'm going to ask myself whether these balance out. So sodium is plus, PO4 is 3 minus. So the best way to balance that out is by adding a 3 to my sodium, so that I've got an overall charge of 3 plus here and an overall charge of 3 minus here. So they kind of balance out. Now what I'm going to do is I'm going to make sure that the number of the number of atoms on my left hand side equal the number of atoms on my right hand side. So the best way of doing that is to look at the lowest common denominator. So if I've got 3 sodiums here and 2 sodiums here, the lowest common denominator is going to be 6. So I'm going to add a 3 here to make sure I have 6 sodiums, a 2 here to also make sure I have 6 sodiums, and therefore, because I've got 2 PO4s, I need to add a 2 here so that I've got 2 PO4s again. And then if you balance that out, that's going to mean 3 CO2s and 3 H2Os. Always remember that the carbon in your carbon dioxide is always going to come from your carbonate ion. So whatever the coefficient is for your for the compound with the carbonate ion, that coefficient is going to be the same for your carbon dioxide as well. Good, so quite a bit of balancing. It's quite key though, that's kind of why we're doing all this practice. Let's look at our last reaction though, acids and bases. So neutralization reaction, here we make salt and water. So we call that a neutralization. Another thing that's worth bearing in mind is that these reactions are exothermic. So a bit of a throwback to topic 5. This means that they've got a negative enthalpy change, and therefore an observation that you might notice is that it releases heat. And although you're quite unlikely to be asked about it because it's not quite a qualitative observation, but it's worth bearing in mind that it releases heat. So let's look at a couple of other chemical reactions to balance out. So we're going to go a little bit quicker through these ones. So HCl plus magnesium hydroxide. Magnesium has a charge of 2 plus, hydroxide minus. Therefore, I'm going to balance that out by adding a 2 at the back of my hydroxide. I'm going to make a salt. My salt is going to be a metal and the non-metal from the acid, so MgCl. Our next question is, of course, is it actually balanced? Not quite. Charge on magnesium is 2 plus, charge on Cl is minus. So it's going to be MgCl2. And then I know that I'm going to make H2O. So to balance this out, because I've got 2 chlorines on this side, I'm going to also need 2 chlorines on this side. So my overall reaction is going to be 2HCl plus MgOH2 gives me MgCl2, and I'm also going to add a 2 there to balance this out. And as a really big top tip, how do I know that I need a coefficient of 2 in front of my water? What's a quick way of working that out? Always remember that water is derived from a hydrogen ion, H+, and a hydroxide ion, OH-. So I know that on the left side, on my reactant side, I've got 2 hydrogen ions and I've got 2 hydroxide ions. So I'm definitely going to have 2 water molecules. They always combine in a 1-to-1 ratio. The number of hydrogens to the number of hydroxides to the number of water molecules. So that's a useful trick to kind of bear in mind. Let's look at this one then. So sulfuric acid, which is H2SO4, plus sodium hydroxide, which is NaOH. So again, we're going to make our salt, which is going to be metal and non-metal, NaSO4. It's not quite balanced because Na is plus, SO4 is 2 minus. So we're going to add a 2 to our Na to balance that out. I'm going to add my H2O over here. Since I've got 2 sodiums over here, I'm going to need 2 2 sodium hydroxides over there, just to make sure I've got the same number of sodiums on both sides. So we're going to use that trick that I was talking about here to spot the number of water molecules. I've got 2 hydrogen ions, 2 hydroxide ions because of my coefficient of 2, and therefore I know straight away that I'm going to make 2 water molecules because they always combine in a 1-to-1 ratio. Good. So that's all about balancing your equations. The other question that you can get in 8.2 is kind of a bit of a calculations question. So it combines stoichiometry and your understanding of acids and bases reaction. So here you're being asked what volume of a 0.8 moles per decimeters cubed solution of KOH, so remember KOH is going to be a base, potassium hydroxide, because it's got the hydroxide ion, would be needed to completely neutralize 30 cubic centimeters of 0.2 moles per decimeters cubed of sulfuric acid. So this is going to be your acid. Perfect. So whenever you see a question like this, you should always balance out the reaction. That's always going to be our first step, right? So let's have a look. So you're going to balance out that equation, and KOH and H2SO4, so you're going to make your salt, which in this case is K2SO4, and you're going to make water. Remember, the coefficient of water is going to be 2 because we've got 2 hydroxides and 2 hydrogens, and they always combine in a 1-to-1 ratio, so 2 to 2 to 2. Perfect. This is really important because it's worth bearing in mind what your coefficients are for your reactants, because that's going to tell us about the number of moles that are reacting. So that's going to be our next step. We're going to calculate the moles. Since we're talking about solutions, the triangle that I want you to bear in mind is the NCV triangle. So working out the number of moles is always concentration multiplied by volume. So this is how I've worked out the moles for the sulfuric acid, so 0.03 times 0.2. This is all information that you've been given here and here. Remember, when you use the NCV triangle, you need to convert your cubic centimeters to decimeters cubed. And the way that we do that is we divide by 1,000. So that's why it's 0.03, which is the number that I've used over here. Based on that, you can work out the number of moles required for potassium hydroxide, because according to our reaction earlier, the coefficient is 2, so it's going to be twice as many moles of H2SO4. So it's going to be 0.006 times 2, which is going to be 0.012 moles. Perfect. So now that we have the moles, we can calculate the volume, again using this triangle over here. So according to the triangle, volume is going to equal to the moles divided by the concentration. And that's exactly what we've done over here. So we get 0.015 decimeters cubed, because we're always using decimeters cubed. But here the answer has asked for centimeters cubed. So we're just going to convert it back really easily by multiplying that with by 1,000. So if you're stuck with a question like this, always remember the 3 steps, right? So you're going to balance out the reaction to kind of work out what the coefficients are of the reactants. That's the first step. Always calculate the moles as your second step. The NCV triangle is really useful. And then you can derive whatever the question is asking you, also based on the NCV triangle. It's always worth bearing in mind what the unit is. So in this case, the unit that they were after was centimeters cubed. So just make sure your final answer is also in centimeters cubed. Perfect. So we are at the end of our video. I've just got a little bit of a summary slide here about the different reactions that we've spoken about and the different products that you can make from them. I'm just going to add a slight note. So we haven't spoken about ammonia at length, But remember that ammonia is a type of weak base. We'll be talking more about this in our video on 8.3, and therefore it's also going to make salt and water. However, the salt is just going to have the ammonium ion in it as well. Okay, so I hope that was useful. Thank you so much for joining us for our video on 8.2. Now, if you're looking for a bit of additional support, don't forget that we also do online private tuition, which is one-to-one, and Lanterna also holds chemistry revision courses, amongst other subjects, a number of times a year. So definitely have a look at our website, and I will see you next time for our video on 8.3 acids and bases. Have a nice day, everybody.